We're very happy to have John to give us a presentation. So some bio about John. John is now a student study at Washington State University. And his major is in material science and engineering, and is a completing mathematical minor at Linköping University in Sweden. I hope my pronunciation is correct.
That was great.
So he's now working in Dr. John McCloy's nuclear, optical, magnetic, and electronic materials lab, and he researches glasses and glass ceramic for nuclear waste immobilization. His current projects involved advanced X-ray characterization as well as the behavior of highlight transition metal and actinide in silicon glasses. Also, he previously worked on cement rock interactions with the CREST team at Vanderbilt University. So I'm hand over the microphone to John. So I'm looking forward to see your nice presentation.
Thank you very much. Let me get my screen shared. Hope you all can see this. Yeah, and it's great to see some of the folks from Vanderbilt. And yeah, so my name is John Bussey, you guys just heard. I'm an undergrad at Washington State, and I'm going to talk about a little bit about some of the work we've been doing on salts in nuclear waste glass. And so this talk is going to be very much down a technical glass rabbit hole. So for all of you that don't do glass, I'm very sorry, and I will try to keep it at least somewhat relevant. So first off, I want to thank the army of folks that supported this work. In particular, this was it started out as at the tail end of the PhD of Natalie Smith-Gray, and Ian Wells has done quite a lot of work on this. And as all good science does, it's been done by quite a large number of folks. And then of course I need to thank my advisor back at WSU, John McCloy, for all of his support and for leading this research. So kind of three main things I'm going to talk about today. First, a little bit of an intro about salt. Most of our work involves the Hanford site. So I'm going to give a little bit of background on that, although I'm sure everyone here is intimately familiar with that site. Then we'll talk a little bit about salt formation in fluorine and chlorine containing glasses, and then kind of switch to a study talking about detecting this salt when it forms during processing. I was told I had to fill about half an hour, so I put together two 15-minute talks I gave in conferences into 1 hour talk. So they're related, but not that related. So I'll try to, hopefully it'll be somewhat sensical. So Hanford, again, I think many of you are familiar with this site, but it's the nuclear waste site in my backyard, being from Washington State. And we have over 50 million gallons of radioactive waste in 177 tanks. These were designed as temporary storage during the operation of the plutonium reprocessing for mostly for military use in the mid-1900s. And one of the unique things about this waste is that at the time, they were still doing much development work on this reprocessing. So there were a variety of different waste streams that formed. And since there were all these different waste streams, they all were put in different tanks, maybe without the best skills at writing them down. And it wasn't 100% clear it was in all the tanks. And so we basically ended up with 177 tanks, each with a different composition, with a variety of different nuclear waste components. So as a result, about 2/3 plus of the periodic table can be found in these waste streams. And since there's such a large volume of waste, it's been diluted with a variety of different components. Most of it is not the most radioactive high-level waste. The majority of the volume is low-activity waste, somewhere about 95% of the volume. That's not actually particularly radioactive. However, by law, they need to vitrify it. So it's turn it to glass is the chosen method. So we need to come up with a method for high waste loading to get as much waste as possible of this low activity waste into a glass. So one concern during the process is salt formation. So While many of the problematic or main components of the waste, aluminum, sodium, have really good solubility and durability in nuclear waste glass, in the glasses used, the borosilicate glasses, there are a variety of components that are also found that are much less durable. And these are often called volatiles, things like sulfate, molybdate, fluorine, chlorine, etc. And so this is one of the main concerns of low-activity waste vitrification. And the reason we are worried about these anions is if they form salts, which is what they like forming salt with a variety of alkali and alkali earth elements. If this salt phase forms, often called yellow phase or gall, it's really quite nasty. And the main concerns are that since it's a very corrosive liquid, and so it corrodes the refractory lining of the melters. But the issue with that is that these melters are $1 million piece of equipment, and so if you have to replace them often, and you can't just replace the lining, you have to replace the whole instrument. But that's possibly the least of the concerning issues of salt. The other issue is that it can cause the way these melters work is they have electrodes that go in the heat the melt through conduction. And if you have a very highly conductive salt layer on top, you'll just short out the melter. Other concerns are these salt phases, as with the names volatiles, they volatilize very quickly and they will go up into the off-gas system, which can be quite difficult to work with. And they're also water soluble upon cooling, and they'll trap things like cesium and iodine, etc. So salt is really, we don't want it, and we've seen that we've had it. This picture up in the top right was from a boxcar test at PNNL where they vitrified a bunch of waste, and you can just see on the top the layers of different types of waste, different types of salt that have formed. So this salt is a key constraint when trying to design these Hanford glasses. And notably, if we're able to figure out how to deal with the salt and what makes the salt form and how to prevent it, we can probably get more waste in the glass, which means cheaper and less volume to dispose of, and it's probably has higher durability. And we also care, not really for this audience, but the geology community cares a lot about the impacts of volatiles on magmatic processes, and oxyhalide glasses have a lot of impact throughout, from optics to biological glasses to be used in medicine. So at the Hanford site in particular, I mentioned that it was a key limitation. So there's formulation rules at Hanford for the low activity waste, for both alkali, so sodium, potassium, as well as with halides. And the study I'm going to talk about kind of targets both of these things. But the interactions between different kinds of salts are not very well understood. And there's been a variety of models that have formed to encourage acceptance of higher waste loadings of salt, because some of these tanks contain significant portions of salt. And so if you're limited to a significant amount of fluorine or chlorine or sulfate incorporation, that's problematic. It's just as kind of a ballpark zone. Generally around 0.8% sulfate is the limit of the older models, although newer models have pushed that to up to double. And then for the halide, again, the halide range here for this is chlorine and fluorine is much lower. So we designed a well, not me, Natalie in her PhD designed this series of glasses to kind of test these things. This is right at the end of her PhD, and I helped her make the glass, and then she promptly left with these pile of glasses and no characterization. So what did we make? They were made at 1200, so slightly above the operating temperature at Hanford, which is 1150. We made them platinum crucibles, and then we made this kind of simulant mixture, so no radioactive elements, and outside of a lot of the more minor components, we chose the main things that affect the glass forming ability, and then varied fluorine and chlorine to test their incorporation. So the first thing we did is we measured the composition. So to start with the chlorine glasses, you can see here on the left that as we added chlorine, the glasses don't really change, but at around 9 mole percent. And just as a side note, the way that these samples are named is the number before chlorine is the mole percent, and that was put in the beginning. And the same thing with fluorine. At around 9%, 6%, we start seeing this salt phase form. It's a big thick layer of salt form on the surface. And around the same time, we observed that pretty much all of the sulfate crashed out. So the chlorine got up to about 3 mole percent loading, very poor, and it drove away the sulfate. So it indicated to us that the sulfur and the chlorine were probably competing for the same components in glass. To kind of understand the structure, we looked at NMR, nuclear magnetic resonance, Raman spectroscopy, X-ray diffraction, and a variety of other methods to try to understand what's going on. In the Raman, the main thing that we observe is we see that as at higher chlorine loadings, all the sulfur goes away, right? That corresponds with what we saw from the elemental measurements. In terms of the NMR, we see that's the N4 peak, which is 4 bonded boron, and as that decreased with chlorine, that indicates that there's less sodium available. The sodium in this case is going into the salt, and so we can kind of, from this plus the picture before, get the sense that chlorine and sulfate are both probably leaving the glass into the salt phase, and they're competing for sodium. This here is a variety of properties. So the density decrease, the glass transition temperature increase, and as we plot that against sodium and chlorine, we see that as you add more chlorine, the density goes down, and against sodium, the less sodium is, the density also goes down. And so again, what this tells us is that as you add chlorine, you remove sodium, and it goes into a salt phase. The sodium goes into the salt phase to charge compensate the chlorine coming in. So that's the primary story here. So for the fluorine glasses, these were much more complex. As you can see on the bottom, as we have fluorine, around 15% mole percent fluorine, the glasses turned opaque. And then they got very white. They looked like porcelain maybe. And looking at X-ray diffraction, it indicates that we have a significant amount of crystals that start to form, around 15% mole percent at the highest fluorine loading. 15 weight percent, excuse me. And so calcium fluoride crystallized first, and then later on sodium and sodium aluminofluorides crystallized later, indicating that the calcium fluoride is probably the most prevalent phase to form. So taking a look at the microstructures, unlike the salt phase up in the chlorine where we got 2 very stratified different salt layers, in the fluorine, what we have instead is these strange spherical-ish micron and submicron sized particles. The calcium fluoride are the biggest, followed by smaller phases that correspond to the other minor crystallites. The key takeaway here is that the excess fluorine, instead of being released as a salt or released as a volatile, is instead retained within the glass. Even though they're crystals, which, depending on what the crystal is not ideal, they're still retained. And calcium fluoride, actually, it turns out there's been some work out of Australia that has shown that calcium fluoride crystals are fairly durable and are probably okay to be in a waste matrix. This question of whether you can have, what crystals you can have, and whether you can have them is certainly ongoing, but calcium fluoride appears to be, unlike something like nepheline or sulfate or a sodium salt, to be something that's more okay. So taking a look at the compositions, here we have kind of in these blue circles so we see the fluorine, and we see that the fluorine is almost entirely retained within the glass or within the glass system. But we know that about 15 mole percent we start forming these crystals, as you see here. However, the way we measured composition, was with electron microprobe. And that method, the smallest spot size we get down to is around 10 microns. Now you see in these images, 10 microns involves a lot more than, you can't just get glass, you get glass and all the crystals. So we know that almost all of the fluorine is retained within the system. But we devised a method using both the fluorine in the crystals, both the fluorine measured that include crystals and glass, and the known weight fraction of crystals from Rietveld refinement of our X-ray diffraction to estimate what the composition change looked like. And so we saw that the fluorine appeared to plateau at around 14% fluorine in the glass, with the rest going into crystal. The other thing to note there is that it turns out, when we look at the composition, that the calcium actually, that these sodium and sodium aluminate phases form only after calcium is entirely depleted. So that's quite interesting. We know from a collaborator's molecular dynamics simulations that fluorine is most highly desired to bond with calcium. So makes some sense. And then taking a look at the structure, these glasses were much more complex. Looking at the fluorine NMR, this is the entire paper that my advisor wrote on a separate subject, but basically it looks like we can assign 5 different environments. So the fluorine, once it gets in the glass, it wants to be with calcium, but it also appears to be relatively happy in a glassy structure with aluminum and sodium as well. And we also looked at aluminum 27 NMR, which indicated that the aluminum was almost always 4 coordinated. However, when we started adding more fluorine, we saw the presence of some aluminum 5 and aluminum 6 coordinated aluminum, and that corresponds to the aluminum in the glass as well as the crystal. The other thing to note here is looking at the Raman. We see that in the fluorine system we retain all of our sulfate, so that peak remains the same. However, you can see that the peak narrows quite a bit. Maybe it goes from a more Gaussian distribution to a more Lorentzian distribution, and with that's maybe indicative of crystallization. So even though we can't see it with the X-ray diffraction, it looks like there's probably some crystalline sulfate that's forming, which is not ideal. That's not really what we want to find. That's also interesting because we see from our compositional measurements that I showed on this slide before that the fluorine the sulfate pretty much entirely stays in the system, which that's great news because it's not forming a macro salt phase. However, the fact that we measure it all, but we see it's getting more crystalline, makes us think that in all likelihood, there's some nano crystalline sulfate. So it could be a variety of one of these phases we observed in our scanning electron microscopy. And here are our fits from the fluorine NMR, and I mostly put this up here because it took a very long time, and I'm slightly happy about making it. But this involved looking through all the literature of all of the fluorine environments ever assigned, and then trying to connect them. But basically, we can show which of the aluminum and calcium and sodium environments the fluorine goes into, and it's fairly strange that the fluorine is in all of these different environments at the atomic scale. And then look at the properties. The properties are a bit more complex, but in short, the density decreases, which makes some sense. As fluorine goes in, it terminates the silicate chains. It forms, it depolymerizes the network, which opens up the network, so it decreases density. Makes sense. So that's item 1. Thermal analysis was much more complex. It's hard to see a trend really with this plot. However, the fluorine initially very much decreases the glass transition temperature, which again makes sense because it's opening up the network, it's causing depolymerization. And then what happens afterwards is a bit more amorphous, if I can say that. But probably it's due to how the residual glass is changing once the fluorine leaves. So what does this mean for hand? This is kind of how I motivated this originally. So The sulfur original, it's called the line model. It's kind of a three-part stepwise function. And this shows that that's probably not the right way to be thinking about it. The fluorine retention, again, it was over 14 mole percent up to almost nearly 5 weight percent just in the glass, plus with at least durable crystals forming for at least a little bit longer. Whereas we found that the chlorine retention is very poor. We found it, we lost about 3 mole percent. So there's that. The other thing to note is that there's obviously a lot of effects with sodium and calcium, which that was previously known, but it's good to know. So this slide's, it's a bit of a mess, but this is basically to look at, try to understand how our glasses fit in with the Hanford models. And basically the end takeaway is that these glasses were right kind of on the line of what would be expected to be allowed at the Hanford waste treatment plant. But they probably shouldn't have been, given that we found salt formation in all of them. And the other kind of, to form over the next subject, a key distinction to be made is that the excess chlorine forms this large salt layer, while the excess fluorine goes into crystals. And that, we're not quite sure we understand why that is. However, it's definitely a significant difference between the two, which, given that they're just one next to each other on the periodic table vertically, it's probably surprising. So next, I'm going to talk a little bit about salt detection. So this salt, if it were to form and be detrimental, it'd be kind of like what happened with the sodium chloride, where it formed a layer on the surface. And little pools of salt, kind of like in this picture to the upper right, is probably okay, but a large layer of salt that covers the whole surface is much more concerning. So it would be really important to be able to tell that the salt is forming before a solid salt layer is formed and the electrodes are shorted out, or before the off-gas system is overwhelmed by volatilizing halide. So you want to be able to try to tell when this salt is forming. And there are a variety of methods that are used to do detection during this melt. There's physical methods, there's electronic methods, they've used magnetic resonance and spectroscopy. There's a line, this overlaps with a lot of work that's done in the molten salt community, looking at molten salt reactors. So there's a variety of ways to be able to detect things that are going on. But in particular, we want to be able to have a remote method that's able to tell if there's salt there. And this problem is difficult for a few reasons. Number one, this is a very caustic, hot environment, and so you don't necessarily want to be sticking things into the melt. It's also, if you think about looking down into it, you'll be seeing there'll be a lot of, since the slurry that is added contains a lot of carbonates and nitrates and tons of water, you'll have a lot of gases coming off the melt, as well as some cold cap. And so you need your detection method to be able to see through those things. So what we decided to work on is this method called millimeter wave radiometry, where you're using waves at millimeter wavelengths, so quite long, and then using them to look at the optical properties, the thermal emissions off the surface of your melt. And this has previously been proposed. A lot of work was already done, most of it led by Waskov out of MIT, looking at this to understand a variety of systems for space exploration, for coal gasifiers, and this was another area where it was meant to use, and they did some initial testing, and they showed that you could see a difference in the emissivity of salt and of glass. And so since this method tells it pretty much from this radiometric signal, you can decipher differences in emissivity. Since they showed that you can see salt, it seems like it might be worth a try. But that was 20 years ago. Nothing's been done since. So Natalie and my advisor dug out this piece of equipment, started getting it set up, and then, as mentioned earlier, Natalie got a job as an assistant professor at Wall Wall University, and she was off to do better things in life, and the rest of us, me, worked on the system. So the goal of this was to try to understand what this would be like detecting this salt in situ. Instead of just taking a measurement of glass and then add salt, actually use it to use it in an in situ environment. So our experimental setup looked something like this. Basically, you have heterodyne receivers that for the radiometry detector and the interferometer. The radiometry detector, again, it detects thermal emissions, and then the interferometer looks at you can tell surface height changes in the surface. And then there's this optical setup with a couple mirrors and a chopper and some different waveguides. This slide here is, I could probably spend 20 minutes explaining how these different calculations work and how we derive them. And you will all be even more put to sleep, and I might still be confused. So we're not going to do that, but the different optical, the key point here is different optical components add complexity to the system. And then we have two radiometer receivers, which is important because based on knowing the difference in the length that they travel, we can gain information on what the emissivity is. And you put the two radiometer values in these equations with some calibration constants and some known constants and some temperature and the temperatures that we measure. And from that, you're able to back out emissivity. And then from that, you're able to bake out a measured temperature of the sample with the radiometer. And of course, we can measure the temperature of the sample with a thermocouple. And so we do that to kind of compare against. So the assumption that we have to make to be able to do this is that transmissivity is 0. So all of the incoming, all of the thermal radiation is reflected off the surface or emitted by the surface. None of it is transmitted through the sample. And so this was probably true for the black glasses this was initially looked for the Savannah River project, where as I mentioned above, Waskov and coworkers worked on it. But for clear glass, maybe this isn't true. And so this is one challenge with this method that I'll talk about here in a minute. So what do our results look like? So we get these curves. So before I go further, our temperature, we used a temperature profile to look at this. Instead of just looking at a fixed temperature, we heated up the melt, held it constant, and cooled it down. And so for a perfect black body that had no reactions or interactions, we'd expect this to look like to be kind of a stepwise function. But these very much aren't that. And so there's some interesting things going on. The calcium fluoride measured reference standard up here on the upper top right, besides the funky portion, is about what we would expect the model to look like. So we measured 4 glasses, a chlorine glass that formed salt, a fluorine glass that formed salt, and then our baseline. But then when we ran the baseline with this test that had no chlorine or fluorine, just 0.8% sulfate, we found some salt that formed. And so we were motivated to make one with no salt of any kind. So our baseline didn't work particularly well, but that's perhaps a interesting feature about sulfate. Again, mentioning that the models are perhaps are too liberal in estimating sulfate presence, and this is another example of that. So we measured those, then we measured a bunch of several reference materials of the salts that we thought might form, and then tried to match them up. And what we saw is that in the glasses that formed a salt, namely the fluorine, chlorine, and the one that just formed sulfate, we see fairly good. Probably the easiest thing to tell is this recoalescence behavior, and we see fairly good agreement between the salt crystallizate, the freezing point, and the values that we observe. And so this is expected. This recoalescence temperature is, so back to this last slide for just a minute. Emissivity depends on a variety of factors, including the thermodynamics of the sample. I don't know why I backed up 2 slides to show you that, and I didn't need to. But the thermodynamics is related to the emissivity is related to the thermodynamics of the sample. And so when you have a phase change of this, when you have a release of heat, we can detect that with and so even this emissivity change, we can tie this with the radiometer. And so we see that the salts form both in the sodium sulfate and the sodium chloride form at a fairly significant undercooling, and which again we'd expect it to be undercooled by 50 or so degrees, which is what we see here. And the other thing to note, or one other thing to note, is that the fluorine, the sulfate detected in the fluoride glass is much higher, and so this maybe suggests there's some maybe sodium fluoride, sodium sulfate binary that's forming, that's causing it to shift to higher temperatures for freezing. A couple other things to note: we melted the glasses directly from powder, like we do at Hanford, the waste treatment plant, and then also melted them once they were all off-gassed with just the melt, and saw similar agreement, but without this feature here on heating, kind of those ripples, and those we think correspond to, well, we are fairly confident they correspond to off-gassing. Some other things we observe is that even when we would expect the temperature profile to be flat, when there's a significant decrease, that is typically corresponding to salt formation. So we're able to do the salt, we're able to see when there's salt forming and do some kind of fingerprinting with these standards we made. So I mentioned most of this, but again, we were able to see this with the millimeter wave, including some things that we weren't able to see with other methods, particularly with X-ray diffraction, but also even though the Raman spectroscopy didn't necessarily immediately pick up some of the things that we observed. Another thing to note is here in the kind of in the bottom right corner, you see an optical microscopy image, and this is of the sample here in blue, dark blue, where we see some of the most clear salt formation. And we found, we looked at the optical microscopy, the salt only covered maybe 20%, 30% of the surface. And so they're forming, instead of forming a large salt layer at these concentrations, they're forming small patches of salt. And so that's a good sign, because that means that means our system is able to detect incipient salt formation, right, when it's first forming, instead of only when it's formed a large significant layer, maybe like an electrical method would. We also get data out of this instrument called interferometry, and from that we're able to look at the surface height changes. And the main feature here is at around 2.5 hours, which is when we reach our top temperature, we see these large spikes, and in each of these kind of humps, it's related to the cosine curve. Each single period of one of these is a quarter of a wavelength, so about 0.5 millimeter of surface height change. And so we were able to connect that with our radiometry and see that, oh, that's exactly when the off gas is happening. Another interesting thing to see is right about at the end of when this finding is happening and when the radiometry starts to decrease. So when we think salt's forming, we see another peak here that we think we can assign to salt formation because we see it in all the salt, all the glasses that form salt, and we don't in the glasses that don't. So the other thing we did is we did some thermogravimetric analysis on the same batch materials at the same temperature profile to be able to connect the weight losses with the surface height change. We found that the majority of the foaming happens only at the very last 1 or 2 sets of carbonate loss, which again, perhaps this is not too surprising because at lower temperatures, the glass is not fused yet, and so it's not reactive enough to form large bubbles. So bubbles only form at the very end of the gas evolution. So ultimately, what we want to do with this method is not just plot radiometry signal, because that's not very physical. We want to try to extract out an apparent emissivity. However, we had quite a few issues with that, and this was not what I hoped to be presenting. I hoped to be presenting very nice, beautiful curves, but that never is really what happens in science, at least in my experience. Although actually things when I was at Vanderbilt were much more effective than most other science I've done. But that's a side note. Some of the main issues we had is we were having detector issues. You can see here on the right, some of these features that I have circled are indicative of issues with one of the detectors. Particularly, it really did not like getting cold, not much below 65 Celsius. And in the winter in Pullman, when it's regularly 0 degrees Fahrenheit outside, oftentimes facilities not keep the buildings warm enough to keep our detectors happy. Another issue we have is the chopper. The motor on the chopper appears to be slowly dying. And since I'm currently in Sweden on an exchange program, I did not have time to recollect the data, but we see that's also introducing some artifacts. And looking at the emissivity is also very difficult because, as I mentioned earlier, we're assuming that transmissivity is not here. And another component, as I mentioned about thermodynamics, emissivity is only really reliable at equilibrium, and the system we're looking at are very out of equilibrium in several ways. So because of that, it's a difficult process. But that was mostly to preface seeing this data that's a bit noisier than we would have hoped, but we were able to extract apparent emissivities for the samples. And this behaved mostly as expected. Again, as temperature goes up, at least in the lower regimes, emissivity goes up. And at these wavelengths and at temperature, we're able to assign kind of a range of what the emissivities look like. And with that, we can probably not only just with the seeing where it freezes, but also seeing the magnitude of the apparent emissivity, we can go and we can probably assign when salt is forming and what the salt is that is forming. We also notice that when you don't have full coverage of the surface, you can only have part of the emissivity that we detect is somewhere in the middle, and that again makes some sense because it's a surface measurement. Now there are several issues with the measurement. Another thing to mention is it's also related to the surface dynamics. So we're probably seeing a convolution of some thermodynamic effects, some surface changes, some of the dynamics of the surface, volume changes, etc. But it appears that we have at least some useful items here. So kind of to conclude, to wrap up some of the things we've been talking about, for the fluorine in calcium, sodium, aluminum borosilicate glasses with sulfur, the foil is always entirely retained. So even at up to 25 mole percent, almost all of the fluorine stayed in the glass. Only 1% or less was volatilized, and none formed a surface salt, which that's good. I'm at a conference right now, and we were talking to a variety of folks about iron phosphates, which were originally thought, which have been thought in the community. It's been somewhat of the common opinion that those glasses are better for retaining halides, but there's been a lot of talk at this conference about how that probably isn't the case, because most folks that do it are only able to retain 5–10% of fluorine in their phosphate glasses. Another thing to note is that this has some potential impact for molten salt waste forms. So that most of, at least in the Hanford world, we're mostly looking at waste that's here that we want to get rid of now. But with the advent of these next generation nuclear plants running up with molten salt coolants and fuels, we will need, in fact, some waste forms. And so this is a good thing to start thinking about for that. And the other thing to note is it had minimal interactions with sulfate. So in terms of a sulfur halide model, they're probably okay. Now, chlorine is not very compatible, in significant contrast to fluorine, in these sodium aluminum borosilicate glasses with calcium. And they have significant interactions with sulfate. It's supposed to be a sulfate. And that is of concern. And they readily form separate salt phases, and they remove sodium from the system, causing this drastic change in properties. All around, unfortunate, probably a poor waste form, and there needs to be more work done looking at the models that are used and using this at Hanford. Back over to the millimeter wave radiometry, this fingerprinting we did was successful. So we showed that it could work in an in situ situation, which is great. We also saw that the interferometry can give us insights into foaming and salt formation, which is also helpful. And we were able to do this at fairly low concentrations of salt with only partial coverage on the surface. So probably can detect some incipient right at the very start of formation. However, the emissivity plots I showed, the apparent emissivity, is really not very attractive, and a good deal of work needs to be done for us to fully understand the processes behind that. From an engineering perspective, this is doing okay from a science perspective. There's a lot of work that needs to be done. There's some more work to do on the fluorine chlorines as well to better understand everything that we have. We do some emissivity. And then a future experiment when I get back to Pullman in January is to start looking at systems like this, but with waste streams more tailored towards molten salt plants. And then if you ask my advisor, he would say I need to be writing all of this. So that's actually the main task. So thank you all for listening and listening to drudgery about glass. And I'm happy to take any questions.
Thank you, John. Nice presentation. So it's time for the questions. So here, my echo.
I should ask a question, maybe because I have missed the part about the little spheres of glass. I was curious if the formation of those spheres are something intentionally that you are doing, like you make them into spheres so they can hold the waste, or just naturally they do that, and that's why you're attracted to glass for this purpose.
So these spheres here, is that what you're talking about?
Yes.
Yeah. So these did not form on purpose. This was uncontrolled crystallization. So generally that would be undesirable. However, calcium fluoride is a fairly durable crystalline phase. And so this is not entirely a problem. Now, that said, there has been work done out in Australia by Dan Gregg and company out at ANSTO, where they've looked at these systems and actually intentionally tried to make these calcium fluoride spheres. So for this purpose. So not necessarily problematic, but we didn't do this on purpose, but maybe an positive unintended side effect, if you will.
Okay, I see. Thank you.
Also, John, can I have a question? So the glass waste here is used in Hanford now, or it's like some hypothetical study of the glass types?
It's somewhere between the two. So the Hanford mobilization plant is in commissioning right now. So it's supposed to be online in the next soon. I'm not going to commit to a deadline because they keep moving it back, but soon. It's in the commissioning phase, but they will start by immobilizing the least difficult tanks. And so the high salt tanks are down the list in terms of urgency, but they will probably be vitrified in the next 10, 15 years. And so this borosilicate glass is the waste form that will be used at Hanford. The exact chemical composition is what they will vary. And for this study is trying to inform how to vary that composition for these compositions.
Okay, sounds good. Yeah, because I'm studying the IDF disposal about the cementitious and glass waste. I think this is really interesting. And I'm doing hydrological modeling, but I think glass formation is also important for me. Yeah, thank you.
It is about a bit outside the normal scope of CREST, but it is some work that is need to be done out here near Hanford.
Okay, any other questions from the audience? Okay, if not, let's give John another applause. Thank you, John, for your great presentation. So thank you everyone for joining, and let's meet like in 2 weeks for another guest talk for CRESP early career seminar. Thank you very much.
Thank you, John.
Thanks, everybody.
Thank
Good
you,
to see
John.
you.
Come back to Nashville.
The weather sounds much nicer.
Well, we need your rain.
Have a good Thursday.
Bye-bye.
Bye.